Welcome to the Deep Dive. Today we're jumping into a really seminal paper. It's called Deep Residual Learning for Image Recognition. Came out of Microsoft Research.
Yeah, this one really shook things up in computer vision.
Absolutely. Our goal today is to kind of unpack the big idea here, how they managed to train neural networks that were way deeper than anything before, and why that was such a game changer for image recognition.
Exactly. This paper, it's a preprint for back in 2015, but its impact, huge. It really set the stage for a lot of the advanced AI image stuff you see now.
So before this, people knew deeper networks should be better, right?
Yeah.
More layers, more complex features it can learn. Kind of like us learning more over time.
That was the basic thinking, yeah. Simple features, first edges, colors, then combine those into more complex things, shapes, textures, eventually whole objects. More layers should mean, richer understanding.
But it wasn't that easy. They hit snags trying to actually train these super deep
Oh,
ones.
yeah, big time. The first major hurdle was this thing called the vanishing or sometimes exploding gradient problem.
Right, I've heard of that. It's like the learning signal gets weaker and weaker as it goes back through the layers, or sometimes blows up.
Precisely. Imagine trying to adjust the start of a long chain based on the final result. If the signal fades out, the early layers just don't learn effectively. It really hampered training deep networks.
Okay, but then techniques like batch normalization came along. Paper mentions that helped quite a bit.
It did. Batch norm was a big step. It helped stabilize the learning process, kind of smoothed out the signals flowing through the network. That let people push to, say, tens of layers, which was already much deeper than before.
But here's the kicker, the really weird part. Even with batch norm helping the gradient flow, just stacking on more layers started to cause a different problem. And it wasn't overfitting, right?
No, that's what's so fascinating. It wasn't that the models learned the training data too well. They actually started doing worse on the training data itself. They called it the degradation problem.
Worse on the training data. That seems backwards.
Totally backwards. Figure 1 in the paper shows it clearly. They tested on CFAR 10, I think. A 56-layer plane network, just layers stacked up, performed worse than a shallower 20-layer one.
Huh. Because theoretically, the deeper one could just learn what the shallow one did and then have the extra layers do nothing, right? Like just pass the information through.
Exactly. It should have been able to perform at least as well. If the best solution was the 20-layer one, the 56-layer network could, in principle, learn that and then just learn identity mappings for the extra 36 layers.
So the fact that it didn't, that the training error increased, it suggested something fundamental was making optimization really hard for these very deep plane networks.
Right. It wasn't the gradients vanishing this time. It was more like the network just struggled to learn even simple identity functions easily across many layers.
Okay, so this is where the Microsoft team had their breakthrough idea, residual learning. How does that work?
The core idea is, well, pretty elegant. Instead of making a block of layers learn the entire desired output, let's call it HX.
Okay, the target function.
Yeah. They said, let's make the layers learn the difference between the target HX and the input X. Let's call this difference FX. So FX equals HX minus X.
The difference, the residual, okay.
Exactly. Then to get the original target HX back, you just add the input X to the output of the layers. So HX becomes FX plus X.
Ah, I see. So the layers are learning the change needed, not the entire output from scratch.
Precisely. And the intuition is that learning a small change, the residual, might often be much easier than learning the whole complex mapping directly.
It's like correcting a photo that's slightly off versus drawing the whole photo from memory. The correction seems way easier.
That's a great analogy, especially if the ideal function HX is actually quite close to the input X, meaning it's close to an identity mapping.
Right.
Then the residual FX the layers need to learn is very small, potentially close to 0.
Which should be easier for the network to learn than a whole complex function.
Exactly. And figure 7 in the paper kind of backs this up, showing the responses on these residual functions tend to be smaller than in plane networks.
So how do they actually build this into the network, these shortcut connections?
Yeah, figure 2 shows a basic block. The shortcut connection or identity mapping literally takes the input to the block, say before a couple of convolutional layers, and adds it element-wise to the output of those layers.
So it just skips over those layers and gets added back in.
Right. That addition creates the FX plus X structure.
And the neat thing is, these shortcuts don't add any extra weights or parameters to learn, right?
Sure.
Or much computation.
Correct. It's incredibly efficient, just an addition operation. It's an architectural change, not really adding complexity in that sense.
Okay, so let's talk architecture. Figure 3 shows the difference plane networks versus these residual networks, or ResNets.
Yeah, planets are just sequential stacks. ResNets have these blocks with the shortcut connections built in.
And the results,
Yeah.
especially on ImageNet, that huge benchmark dataset.
Dramatic. Table 2 and Figure 4 really tell the story. Remember the degradation problem. The 34-layer plane net did worse than the 18-layer plane net on ImageNet. Higher error.
Right, deeper was worse.
But then look at the ResNets. The 34-layer ResNet performs significantly better than the 18-layer ResNet. Lower error, both training and validation.
Ah, so the residual connections fixed the degradation problem. Deeper was better again.
Precisely. It showed residual learning was effectively letting them train deeper and actually get the benefits of that depth.
And they didn't just stop at 34 layers. They went much deeper.
Yeah, they went up to 152 layers, which was like 8 times deeper than the VGG networks that were state-of-the-art at the time.
152 layers. Wow. And was it super computationally heavy?
Get this, the paper actually points out that their 152-layer ResNet had lower computational complexity, fewer FLOPs, than the shallower VGG16 or VGG19 nets.
No way. Deeper but more efficient.
How they used some clever design like bottleneck structures in the deeper blocks, but the core residual idea allowed that depth without ballooning complexity like simply stacking VGG layers would have.
Okay, that's impressive. And the performance.
Phenomenal. Tables 3 and 4 show huge jumps in accuracy on ImageNet as they went deeper with ResNets.
And this led to them winning the big competition that year, ILS-VRC 2015.
Yep. They won the classification task with an ensemble of these ResNets, achieving a top 5 error rate of just 3.57%. That was unheard of at the time, well beyond human performance on that specific task setup.
Incredible. Did they test it on other data sets too, like CFAR?
They did. Figure 6 shows similar results on CFAR 10. Plane nets degraded with depth, ResNets didn't nearly as much, and they could train them incredibly deep.
How deep on CFAR?
They actually trained one with, wait for it, 1,202 layers.
1,200, seriously.
Seriously. It achieved very low training error, showing the optimization worked even at that extreme depth.
But how did it do on the test set?
Interestingly, the 1202-layer one had slightly worse test error than a 110-layer ResNet on CFAR 10.
Ah, okay, so maybe hitting overfitting limits there, even with ResNet. Training super deep might still require care, especially on smaller data sets.
Exactly. It wasn't magic bullet for everything. Optimization was solved, but generalization, overfitting, that's still a challenge, especially when you push depth that far.
Yeah.
Still, training it at all was remarkable.
Definitely. But the impact wasn't just about getting better classification scores, was it? This residual idea spread.
Oh, absolutely. The paper showed it wasn't just a trick for classification. They applied ResNets, specifically ResNet 101, as the backbone for object detection, using the faster RCNN framework on the QoCO dataset. Big improvements, like a 28% relative gain on the main QS metric compared to using BGG backbones. It showed the features learned by ResNets were just fundamentally better for other vision tasks, too.
So better features lead to better results downstream. Makes sense.
Yeah, and they basically swept the 2015 competitions. First place in ImageNet detection, ImageNet localization, QoCO detection, QoCO segmentation. ResNet was the key. Tables 7 through 11 lay out all those wins.
Even localization, just drawing the bounding box, got better.
Significantly better. Tables 13 and 14 show a big drop in localization error compared to previous methods like VGG or GoogleNet. The features were just more precise.
Wow. Okay, so wrapping this up, the big aha moments seem to be, first, this weird degradation problem, deeper herding training.
Yeah, totally counterintuitive.
And second, the elegant fix, residual learning. Using those simple identity shortcut connections, let them break through that depth barrier.
That's the core takeaway. It fundamentally changed how people thought about building and training deep networks for vision. It just unlocked so much potential.
It really addressed a huge bottleneck, didn't it? Feels like it paved the way for a lot of the AI progress we've seen since 2015.
No question. It allowed the field to scale up models in a way that just wasn't practical before. These incredibly deep models are now standard across so many areas.
So here's something to chew on for you, the listener. It's amazing how sometimes a relatively simple architectural tweak, like adding a shortcut connection, can lead to such a massive jump in capability.
It really makes you wonder.
Right. What other big limitations that we currently face, maybe not just in AI, but in other complex systems, could be overcome with a similarly clever, maybe even simple, reframing of the problem?
Uh-huh. Think about it beyond images, maybe in understanding language or complex biology or even, I don't know, financial markets. Where could training much deeper, more complex models unlock new insights if we find the right architectural keys?
Definitely food for thought. And if you want to dig into this more.
Yeah, definitely look up some of the context. Concepts like vanishing gradients, batch normalization are key. Also, maybe check out the architectures they compared against, like VGG and GoogleNet. It gives you a richer picture of why ResNet was such a leap.
Great suggestion. It really helps appreciate the breakthrough.